let's take a look at this idea of partial sums of a sequence. Remember we said like the third partial sum is the first term plus the second term plus the third term of the sequence. And that's a good way of looking at it. Another way to look at it is to say S3 is, well, the first term plus the second term, we've already thought of that. That was the second partial sum. So we can say my new value is my previous value plus that new term I'm adding. And I like this because it gives kind of a sense of we're building on what we've already got before. Things are changing. It's related to integrating, saying my new value of the integral of the area so far is the previous value plus this, this new box that I'm adding. So it's a good way to think about, both of them are a good way to think about things. Let's do partial sums of the sequence 1 over n. So that's 1 over 1, 1 over 2, 1 over 3, 1 over 4, etc. How do you think things go if you start adding those up? So this is just 1. This is just a sub 1. This is the previous value plus the new value. This is the previous value of my sum so far plus the new value. So I'm doing things this way rather than this way. I'll show you this later, but it's a little more complicated in Excel. So let's see, as I'm adding up the numbers, 1 over 1 plus 1 over 2 plus 1 over 3 is that, plus 1 over 4 is that, plus 1 over 5 is that. How do these numbers seem to be behaving? Well, they seem to be growing. I've got a few hundred rows here, just 100 basically. So is this growing to infinity? That's a big question. It's not a bad idea to plot this, so let's plot it like that. Oh, zoomed out too much. So here's the blue is my a sub n, that's my sequence, and then s sub n, the partial sums, is doing that. Does that look like it's going to eventually get close to some horizontal asymptote and never go above it? Or does this look like it's going to just keep going all the way to infinity eventually and eventually surpass any bound you try to put on it? So that's a big question that we're going to be asking. Let's put this over here. So that was 1 over n. We can do 1 over n squared. You can see we're just taking n, squaring it, dividing 1 by that. And then I'm doing the same thing for my partial sums here. So what do you think that behaves like as we sum out to infinity? Does that look like the partial sums are getting close to an asymptote? We can go look at the values down here. It does seem to be growing much more slowly than it did at the beginning. But you know, here, this is also growing pretty slowly, right? Not much of a difference between those two. So it's not entirely clear, will this series, which is the limit of the partial sequences, partial sums, will that converge, or will that eventually grow to infinity? Then I've got another series here that we'll play with a lot in later videos called the geometric series. We're taking some constant, here it's r, 0.9, and we're raising that to the n. So we're doing 0.9 to the 0, 0.9 to the 1, 0.9 squared, etc. And this series by default starts at 0, so that's why I have this in yellow as kind of a warning, like, hey, something different is going on here. And then let's look at the partial sums, just starting with the first term, the second term, the third term. And what do those seem to be doing? Does that seem to be converging on something, or is that going to eventually grow and maybe surpass 10? That's a good question. Let's take a look at that graph. Seems to be approaching a horizontal asymptote. Can we say what that horizontal asymptote is? Based on the value of r, does it even change with r? If I use 0.2, then that seems to be converging, the series seems to be converging to something a lot less than 10, so apparently r does make a difference there. What if I use 1.1? Then all of a sudden this series, the partial sums of the series seem to be growing even faster and faster. What if I use negative 1.1? That might be fun. There, it's oscillating back and forth, but the amplitude is getting bigger each time, so that seems unlikely that it's going to settle down. And we could even try like negative 0.6, for example. And that seems to oscillate but settle down to a non-zero value. Can we predict what that non-zero value is? All interesting kinds of questions. And then we have one more sequence here, 1 over n factorial, which we kind of saw in the Taylor series, Taylor polynomials. So just 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial. And how is that behaving? Is that approaching, seems to have leveled out pretty quickly. So we wouldn't hurt to graph that. So chapter 8.2, we're thinking about this limit of partial sums. Is that approaching a finite value? Can we say what it is? Or is it zooming off to infinity like it was over here when we had 1.1? And then over here, this was growing and it was slowing down, but it wasn't clear whether those partial sums were going to eventually grow to infinity or eventually level out like this one did. Let me show you real quick how we would do the partial sums in Excel with this frame of mind rather than that frame of mind. You don't have to do this, and in fact it's computationally less efficient than the way I've already shown you, but it does link to the math notation that we do in a little bit better of a way. So here we just had this number, and then we said take the previous value and add this. Another way to do that is to say, hey, let's sum a1 and a2. So I might say equals sum of these two things. Notice I have a colon there saying from this starting location to this ending location. I don't have a comma because that would just say this cell and that cell. And if I filled that down, then what is it doing here? It's still just doing it in 2 cells. It's not starting all the way back here. And the same thing here. What I need to do is tell it, when you move down, update this reference so you're summing more and more things, but keep starting at the very top here. So I'm going to do that by putting a $sign in front of the 8 to lock the row. And now if I fill that down, it's using a window that, here the window is size 4, here the window is size 5, etc. So that's more this way of thinking about it. It's less computationally efficient because it's adding up all 3 numbers, and here then it's adding up all 3 numbers again and then adding one more, and then here it's adding up all those again and adding one more. So it's slower. It doesn't really matter in Excel for this kind of thing, but you might wonder, do I still have to have that that formula here that's different than all the rest? And you can actually copy that formula and paste it here. And now it's just summing, starting here and ending here, and that's still the right thing to do. So that says the partial sum of S sub 1 is just A sub 1. So that's another way to think about it, and now we'll turn back to writing these partial sums in paper and pencil notation.